The blistering, sun-baked landscape of the American Southwest. The year 1974. The morning shift is aggressively pushing hard to feed the massive primary crusher deep in the copper pit. An operator commands a bizarre, towering machine up a steep 8% grade that looks significantly less like a traditional mining haul truck and much more like a heavy, armored military transport. It possesses 3 distinct axles and 6 massive wheels. The operator's cab is perched unusually, terrifyingly high, sitting right next to an aggressive, boxy radiator grill. As the massive truck negotiates a sharp, treacherous switchback covered in deep, rutted mud, the 4 rear wheels articulate completely independently, maintaining absolute, perfect ground contact across the jagged, uneven rock. This is the legendary WABCO 3200B Haulpak. It is absolutely not a fragile experimental prototype. It is a brutal, primary production machine hauling exactly 235 tons of raw copper ore. In the early 1970s, desperate mine operators faced a severe, absolute mathematical constraint. They absolutely needed to move significantly more heavy tonnage per single cycle, but the industrial rubber tire technology of the era had reached its absolute, catastrophic physical limit. If ambitious engineers simply built a much larger, standard 2-axle truck, the immense, crushing weight, concentrated strictly on the 4 rear tires, would instantly cause them to violently overheat, delaminate, and catastrophically fail right under the massive payload. Brilliant WABCO engineers boldly solved this massive problem by redesigning the entire geometry of the haul truck from the ground up. They completely abandoned the standard 2-axle format and boldly added a 3rd axle to the rear, creating an innovative tandem drive system. By intentionally spreading the brutal, fully loaded weight of the massive machine across 6 heavy tires instead of just 4, they instantly, mathematically reduced the ground-bearing pressure and the deadly thermal load on the rubber. It was a highly brilliant, radical solution to a severe chemical limitation. But managing the harsh mechanical reality of a massive, 3-axle hauler on steep, twisting mine ramps rapidly introduced an entirely new, highly dangerous physical problem. What exactly happened to the rigid, heavy steel frame of a 235-ton truck when 4 completely independent rear wheels forcefully attempted to track across jagged, completely uneven bedrock simultaneously? To successfully carry 235 tons of shifting payload over the uneven, blasted rock of a deep copper mine, a highly rigid truck frame would simply violently shatter into pieces. The massive chassis absolutely had to flex. WABCO cleverly utilized a highly unique hydraulic suspension system to carefully handle the massive torsional stress. But the true, undeniable mechanical innovation was the massive walking beam directly connecting the 2 rear axles. Instead of solidly mounting the 4 rear wheels directly to the rigid frame, they were attached to pivoting, massive steel beams. If the leading rear tire suddenly struck a solid, 2-foot-tall boulder on the haul road, the tire would rapidly lift, but the heavy walking beam would smoothly pivot, instantly transferring the massive downward load straight to the trailing tire. This brilliant mechanical action physically cut the violent vertical displacement of the truck frame perfectly in half. The massive load remained incredibly stable, and the 6 tires maintained absolute, constant contact with the earth. It was a fluid, almost organic movement for a brutal machine weighing hundreds of thousands of pounds. How did WABCO physically deliver massive engine power to 4 independently articulating rear wheels completely without violently tearing the heavy drive system apart? delivering massive diesel power to four heavy rear wheels that were constantly, aggressively moving vertically relative to the truck frame was technically absolutely impossible with traditional mechanical drive shafts and rigid universal joints. They would simply bind, violently twist, or completely snap right under the extreme torsional load of 235 tons. WABC brilliantly solved this with an advanced diesel-electric system, successfully adapting massive locomotive technology directly to the harsh mine environment. A roaring, massive 12-cylinder General Motors EMD engine directly powered a massive AC generator. Thick copper cables, heavily wrapped in thick insulation and carefully routed exactly along the flexing walking beam, sent massive electrical current directly to four completely independent DC traction motors. One motor was integrated directly into each of the four rear wheel structures. This highly advanced configuration allowed absolutely infinite vertical articulation, completely without mechanical torque wrap-up, as there was absolutely no rigid mechanical linkage physically connecting the wheels. But perfectly synchronizing four independent DC motors on steep, highly twisting mine ramps immediately introduced a highly complex operational variable. If the leading rear motor was spinning slightly faster than the trailing motor on a very tight turn, it would physically push the second axle, causing severe, rapid tire scrub and highly accelerating the gear wear deep in the hubs. Maintenance foremen absolutely hated perfectly calibrating the delicate electrical balance. Operators physically felt this internal mechanical fight as a subtle, hunting vibration deep in the chassis while slowly climbing the steep grade with a full, heavy load. A highly skilled operator could successfully manage this on dry rock. But what exactly happened to the physics of the massive machine when two of those four independent electric wheels completely lost traction on a steep ramp heavily covered in slick southwestern mud? Losing traction with four independently powered electric wheels on a highly slick ramp was an absolute operational crisis. The WABCO 3200B had absolutely no modern computerized traction control. It relied entirely, exclusively on the sharp sensory integration of the human operator. When the leading rear axle suddenly hit a deep patch of unyielding southwestern mud and violently broke traction, that specific DC motor suddenly experienced absolute zero resistance and aggressively surged in rotational speed, its analog ammeter needle dropping instantly to absolute zero. The immediate physical result for the massive machine was a violent mechanical lurch. The walking beam suspension, brilliantly designed to physically stabilize the load, now instantly became a severe liability as the grip vanished entirely from one axle, violently shifting the intense weight distribution. If the operator was slightly too slow with the heavy dynamic braking, the trailing axle, which still possessed solid traction, would aggressively over-torque, potentially shattering an expensive final drive gear into pieces. An experienced WABCO operator absolutely didn't just casually drive, they actively felt the raw voltage. They constantly read the dynamic braking grid temperature. To successfully regain lost momentum, they had to simultaneously perfectly feather the throttle to slightly reduce total DC current and subtly, smoothly engage the dynamic braking just exactly enough to create artificial resistance strictly on the spinning leading axle. This highly specific action forcefully forced the massive EMD generator to send torque backward, straight via the walking beam, to the trailing axle that still possessed traction. It was a fluid, high-stakes kinetic ballet involving hundreds of tons of metal. But this raw mechanical ballet was only relevant if the mine engineers successfully executed the absolute most critical downstream variable in the entire open-pit system. What exactly did the sheer existence of this 235-ton tandem anomaly reveal about the strict limitations of the primary electric mining shovels officially assigned to load it? To properly justify its immense diesel fuel consumption and massive tire replacement costs, the WABCO 3200B had to be loaded incredibly quickly, but the long, three-axle tandem design created a highly unconventional, frustrating target for the highly skilled shovel runner. Because the massive payload weight had to be perfectly distributed over 6 wheels, the heavy dump body of the Haulpak was stretched incredibly long compared to the compact, deep boxes of standard, two-axle trucks. In the early 1970s, the absolute standard primary loading tool in a deep copper pit was a 15 to 20 cubic yard electric rope shovel. When a standard, short two-axle truck rapidly backed directly under the massive shovel, the skilled operator simply centered the heavy dipper and confidently dropped the load. But the extended canopy and stretched steel bed of the WABCO completely altered the entire geometry of the loading face. If the truck spotted normally, the shovel runner absolutely could not reach the rear third of the stretched dump body without dangerously overextending the heavy dipper arm, actively risking severe structural stress directly on the steel boom. To successfully fill the truck completely evenly and maintain the highly precise weight distribution required by the sensitive walking beam suspension, the haul truck operator had to execute a highly frustrating maneuver known as a split spot. They would carefully back in, receive the first 3 heavy passes right in the front of the bed, and then physically pull the massive truck forward exactly 10 feet so the shovel could safely finish loading the rear. This double spotting completely destroyed the shovel's highly efficient cycle time rhythm. It firmly proved that simply building a much larger truck was absolutely useless if the primary shovel could not efficiently load it. But once it was fully loaded, how did the mechanical steering linkage actually handle the sheer, terrifying inertia of guiding 235 tons of heavy copper ore back down the steep mountain? Guiding 235 tons of rolling mass straight down a steep, twisting ramp is entirely, completely dependent on front-wheel traction. The WABCO 3200B suffered from a highly severe physics problem known accurately as understeer. The massive tandem rear axles, housing 4 electrically driven wheels, produced immense, relentless forward propulsion. When the operator confidently turned the steering wheel to carefully navigate a sharp switchback, the 2 front tires correctly angled directly into the turn. But the sheer, unstoppable forward momentum of the 4 heavy rear wheels simply wanted to forcefully push the truck in a perfectly straight line, actively shoving the angled front tires violently sideways across the sharp gravel. To forcefully make the front tires bite hard into the crushed rock and actually turn the massive vehicle, the truck desperately required an immense amount of heavy weight located directly, perfectly over the front axle. WABCO engineers intentionally positioned the heavy 12-cylinder EMD diesel engine far forward and pushed the operator cab out right over the left front tire to physically shift the vital center of gravity. But this specific geometry created a brutal, exhausting environment for the human operator. Sitting directly over the stiff steering axle meant the operator completely absorbed every violent, jarring shock that the front tires encountered. They absolutely did not have the luxury of the smooth hydraulic walking beam suspension safely beneath them. To successfully survive a brutal 12-hour shift without accidentally running the massive truck off the safety berm, veteran operators actively learned to aggressively steer with the throttle. They momentarily, intentionally, backed off the DC power right when entering a sharp turn to aggressively transfer heavy weight directly to the front tires, forcefully making them grip the dirt right before the massive rear tandems pushed the truck straight toward the fatal drop-off. It was an exhausting, highly physical, incredibly stressful method of driving. This relentless mechanical battle against severe understeer heavily, rapidly wore the front tires. But as these unique trucks slowly aged through the late 1970s, the true, fatal flaw of the entire tandem design finally emerged clearly in the busy maintenance bays. What exactly happened when the internal, hidden components of the massive walking beam suspension finally began to fail under the constant, abrasive dust of the deep copper pit? The theoretical, engineering brilliance of the tandem walking beam suspension was completely overshadowed by the harsh, daily reality of its maintenance. A standard, simple, two-axle haul truck required regularly servicing 2 rear electric wheel motors and a single, highly rigid axle housing. The massive WABCO 3200B completely doubled the complexity of the entire final drive. It possessed 4 independent DC traction motors, 4 heavy planetary gear reductions, and the massive, constantly pivoting walking beams that physically connected them all. As the massive trucks rapidly accumulated operating hours in the harsh, dry copper pits, the constant, highly abrasive rock dust slowly infiltrated the heavy pivot joints of the walking beams. The heavy steel pins slowly began to wear highly asymmetrically. When the massive pins wore down, the entire heavy tandem assembly lost its strict, necessary alignment. The 4 rear tires were absolutely no longer tracking perfectly parallel with the heavy chassis. This microscopic, invisible misalignment resulted in immediate, catastrophic tire wear, known to mechanics as scrubbing. The massive rear tires began actively dragging laterally against the sharp bedrock instead of rolling cleanly. A brand new set of 6 tires was a massive, staggering capital expense, and the WABCO fleets rapidly began consuming rubber at a highly accelerated rate that absolutely horrified mine planners. The exhausted maintenance crews were heavily forced to constantly pull the massive trucks completely off the bench to replace the heavy pivot pins, fully rebuild the planetary gear sets, and precisely recalibrate the highly sensitive electrical synchronization of the 4 rear motors. The mechanical downtime skyrocketed out of control. If the highly advanced tandem axle design was proving far too incredibly complex and expensive to actively maintain in the field, what did this actually mean for the ultimate future of 3-axle haul trucks in American open-pit mining? The WABCO 3200B was a brilliantly engineered, completely necessary mechanical workaround for a highly specific chemical limitation. In the early 1970s, the global rubber industry simply could not successfully cure a tire large enough to safely carry 235 tons on a single rear axle without the intense internal friction completely destroying the plies. The 3-axle tandem design was the absolute only way to confidently break the 200-ton payload barrier. But while tired WABCO mechanics were heavily rebuilding planetary gears and constantly replacing heavy walking beam pivots, massive companies like Michelin and Goodyear were fundamentally, permanently changing the advanced chemistry of heavy industrial rubber. By the late 1970s, the successful introduction of massive, highly heat-resistant radial tires, specifically the 360051 class, completely changed the harsh mathematics of the pit floor. A simpler 2-axle truck could now confidently carry 170 and eventually 200 tons, entirely without melting its rear rubber. The heavy mechanical penalty of the tandem axle was absolutely no longer justified. Why maintain 6 completely independent electric wheels, highly complex walking beams, and exactly double the expensive planetary gears if a significantly simpler two-axle truck could easily carry nearly the exact same payload with a tiny fraction of the expensive downtime. The massive WABCO had brilliantly solved a physical problem that the tire manufacturers subsequently completely erased. The entire industry correctly realized that the absolute future of high-volume haulage lay in two massive, highly reliable axles, absolutely not three complex ones. The rigid, highly reliable two-axle electric haul truck, strongly championed by Unit Rig and later Caterpillar, officially became the absolute, uncompromising standard of the mining industry. The massive three-axle trucks that had once boldly represented the absolute cutting edge of high-volume haulage were slowly reduced to rolling, cannibalized donor frames. The veteran operators who had perfectly learned to steer with the throttle, battling the severe understeer to physically force the heavy front axle through sharp corners, found themselves smoothly transitioning to conventional two-axle trucks. The newer, lighter trucks felt comparatively incredibly simple and highly maneuverable. What the incredibly detailed maintenance records actually showed about exactly how they had been specifically operated, which massive machines had been managed well, which hadn't, exactly what the experienced operators had done differently, with the throttle to successfully survive, the brutal understeer went completely away when the operators eventually retired. Some of it was roughly written down, entirely in the form of informal, greasy shift notes and brief maintenance observations that someone quietly thought to keep, but most of it wasn't. If you ever ran one of these massive trucks or proudly engineered one of these highly complex operations, please tell us in the comments. We read every single one. If you successfully operated a three-axle WABCO in a deep copper pit, what was the absolute specific physical vibration that warned you the heavy walking beam was finally failing? The most complete, accurate operating manual for these massive machines is safely locked in the tired heads of the people who actually ran them. Most of it was simply never written down.